Hello everyone, this is Mr. Kozlowski and welcome to Unit 6, Lecture number 2, Learning Target number 2. And today what we're going to be discussing is thermal expansion. So here's the learning target. Students are going to have to explain temperature and thermal expansion in terms of particle motion. So we've already discussed particle motion and kinetic theory in our last learning target. We went over that quite extensively. Now what you're going to do in this learning target is basically apply it to thermal expansion. So let's review kinetic theory. Under regular conditions like room temperature, specific types of matter are going to be found in a solid state, liquid state, or gaseous state. And this is purely dependent on particle motion. And we call this theory kinetic theory. And basically understand that particles are in motion, matters have particles, and their motion determines what phase or state of matter that object is in. So kinetic theory, how is this developed and a little history behind it? Well, we know that all particles are in all states of matter are in motion. This was developed in the 1800s and explains behaviors of gases, solids, and liquids. And part of that behavior is determined by the temperature. Temperature, again, is the measure of average kinetic energy of particles in an object. So if you look at a thermometer throughout the day, or check the weather, check the temperature, basically that is a measure of how fast the air particles are moving in the atmosphere. An object is going to move, and its particles will move faster as a result of the kinetic energy that is increased. So if you increase the temperature, you're increasing the kinetic energy, the motion of the molecules. If you decrease it, likewise, you're going to decrease the motion of the particles. This leads into the concept I really want to talk about today, which is called thermal contraction and expansion. And like I said, you're going to have to apply that kinetic theory in this concept. So basically, this learning target is application. So, for example, let's ask a few questions here. If in the wintertime, why does tire pressure decrease a lot for a car? Well, it's very simple. It goes back to kinetic theory. Those particles are slowing down. Those air particles in the tire are slowing down. Therefore, your tire is going to lose pressure because they don't take up as much space because they're not moving around anymore. Why did they decrease? Why did they not do that? Well, the temperature decreased, there's less energy, they're not going to be moving as fast. On the other hand, let's say you had boiling water. Why does water move when water is boiled? Well, you're adding energy to those particles, you're causing them to move faster. They're basically going through what we call thermal expansion, and that's why it's going to cause a boil. Now, thermal contraction, thermal expansion, you're going to get a spreading out of the particles. In expansion, you're going to get a more tight, less distance between the particles in thermal contraction. And a lot of people have that misconception. So let's kind of talk about this. Thermal contraction. If we look at thermal contraction, this is when temperature decreases and particles will not have much kinetic energy. Therefore, they do not move as far and stay closer together. This can decrease the size of an object like a car tire or a balloon. So for example, we talked about this early on here, where you had, let's say this was particle A. And let's say this circle was particle B. And we talked about this distance. This distance is going to decrease. So kind of in sound waves where we said this distance is going to decrease, the way it's going to travel faster. Well, in this case, the distance is going to decrease. The volume in which that object takes up is going to kind of shrink because of the particle spacing. The particle spacing decreases. The particles themselves do not get smaller, and that is a big misconception. So please keep that in the back of your head that when we talk about thermal contraction and expansion, we are talking about particle spacing. If we go to the next slide here, let's talk about expansion. Well, expansion is the opposite of contraction. So when temperature increases, this is going to increase the kinetic energy and particles will want to move more. Therefore, the particles will move farther apart and faster, thus causing the size of the object to increase. So, for example, a thermometer. What happens when you increase the temperature? The thermometer goes up because those particles are getting further and further apart. So in this case, if we had a drawing here, just like we had similar to the last unit, let's say this is the particle, this is particle A, and let's say this is particle B. The size of the particle should stay the same. However, in this case, in thermal expansion, these particles are going to get further apart. So as more energy goes into the system, say this is energy, particle A and particle B are going to get further and spread further apart from one another. And that's essentially what we have going on in thermal expansion. So what are the applications to this process? What do we need to know specifically? Well, it's quite simple. Here are some examples. If we look at the top, what is thermal expansion? Why do I need a thermal expansion tank? Well, basically, this graphic simulates boiling water. If you look, we start at 70 degrees Fahrenheit. We increase the temperature over 100 degrees from the first picture to the third picture on the right. Well, what is happening is you are adding energy, you're increasing the temperature. Those particles are going to start moving faster and they're going to get further apart, thus thermal expansion. This also happens a lot of times in Wisconsin on the highways and during the summer months where it gets extremely hot, extremely fast. If you notice, this picture is a picture of concrete buckling. In the summertime, this happens because what happens is the concrete is heated, energy is added to the system. Those particles are going to spread further apart and get further away from one another, and therefore you get this buckling. They spread out and the particles buckle into each other. So this is what causes that concrete to kind of almost what you would consider explode on the highway on hot summer days. The opposite could be said for cold winter days right here. And this is a picture of what you would probably classify as a pretty big pothole. And that happens because of thermal contraction. That particles on a cold day, they're actually going, the distance between them are actually going to get closer together and they contract, and what you actually see is the contraction part, or the road essentially getting smaller. In reality, it's just the distance between the particles getting closer together. This also happens right here in the wintertime, especially in Wisconsin. When it gets colder out, your house and the materials in your house, the wood, the plaster, the walls, you might hear some cracking going on and your house makes noises, and that's because thermal contraction is occurring as well. And when your house starts to heat up from the winter months, you're also going to get some of that too from thermal expansion of the particles. So those are just a few examples of many that we could have in class, and we're going to look at this more particular in a lab situation when we get to it. But just understand that this learning target is about practically applying kinetic theory to everyday occurrences and using and understanding those concepts of thermal expansion and contraction. So to review, again, understand the basic concepts of thermal expansion and kinetic theory and apply those concepts of thermal expansion and kinetic theory to everyday occurrences in the real world. We will get plenty of practice in this with our thermal expansion activity that we're going to do in class. Again, only take notes on this one for this unit. Make sure they're good quality notes and you have good examples written down. That's what I'm going to be looking for when I check this for completion in class. And again, if you have any questions when we review over this in class, make sure you ask me. Thanks.